Hello everyone, welcome to my presentation, Backpropagation in Neural Networks, a Mathematical Approach. My name is Carlos Esteves. I'm a data scientist from the SME University in Texas. This video or this presentation is part of my final project in machine learning 2. The objective of this video is to give you an overview of backpropagation and why it's important. I believe that knowing this algorithm will play an important role in your understanding of the entire ecosystem of deep learning. We will explore the different concepts and elements, including the basis of linear algebra, calculus, right? The important derivatives that you need to know in order to understand the algorithm. And more importantly, we will explore different examples, right? You don't need to know PyTorch or TensorFlow. Even though at the beginning I will give you some examples, right? But this is going to be like an introduction, because we will build our own neural networks using simple Python, right? I remember that when I came to this area the first time, I have to go through a lot of things, right? I have to read a lot of materials on the internet, even though I have a great foundations of calculus, but it was not the same linear algebra. So I have put everything together. I have tried to put everything together in this video, so you don't have to go through the same thing. Well, I hope that you will enjoy this video, and let's go to the next slide, and welcome. Now let's explore the agenda. First of all, I will give you a brief introduction of neural networks. Then I will explain important concepts of linear algebra, right? We will create the foundations first. Then we will explain important elements of differential calculus, right? And the most important derivatives you need to know beforehand. Then this one is really interesting, right? Why are we including logistic regression and cost function? It turns out that we can create an analogy between a simple neural network and logistic regression, right? If you have previous knowledge of logistic regression, you will find this really interesting. Moving forward, we will speak about gradient descent, right? Important part. Then vectorization. Vectorization can be part of linear algebra, but I wanted to put this over here because in some ways it's related to gradient descent, right? We will see why when we get there. Then I will explain you the neural network representation that we would use to explain backpropagation. Right? Activation function, right? One of the most important pieces of a neural network, right? Every hidden unit or every neuron, right, has an activation function, and we will see that. And finally, backpropagation. I would like to highlight that we will also see forward propagation, right? Random initialization in this part of the agenda. I mean, we will see different elements in this part. It's not just backpropagation. Well, let's move to the next slide. What is a neural network? A neural network is a computational model, as we can see here, that is inspired by the way the biological neural networks in the human brain process information. However, I would like to highlight that this concept was the initial inspiration. However, this is not the way it works. There are several people that they want to try to make an analogy, right? That in some way they are similar. They are not similar, right? A biological neuron actually is very different from this, right? I mean, there are some elements and some aspects, especially in visual recognition images, right, that maybe we can think they are similar, but we don't know, right? Our brains are more complex, and I would like to highlight that from the beginning. A neural network consists of interconnected units called neurons, right? However, I would refer as hidden units most of the time. These units are organized into different layers, as we can see in this image, right? We have input layers, we have hidden layers, and we have output layers, right? These are the principles. Each neuron receives one or more inputs, right? Process them through an activation function and passes this information to an output function. The connection between the networks have an associated weight and bias, right? We will see that at the end of the day, what backpropagation will do is that it will try to manipulate these weights and bias, right, in order to optimize what we call a cost function. Okay, let's go to the next slide. The universal approximation theorem. I wanted to include this topic here because I think this concept is one of the most exciting and interesting idea of the entire ecosystem of deep learning or complex neural networks. One of the most profound properties of neural networks is their ability to approximate any continuous function. And think about that for a moment, because we are not talking only linear continuous function, but non-linear continuous function, right? And most of the problems, complex problems that we have today, including voice recognition systems, image recognition systems, as we will see in a couple of slides later, they have a high level of non-linearity, right? And neural networks, they are special for this kind of problems. This theorem states that a feed-forward network with a single hidden layer containing a finite number of neurons can approximate any continuous function given a sufficient neurons in the hidden layers. This is really, really powerful, and we will see an example right now. Okay, let's continue talking about the universal approximation theorem. By the way, you can access this book online. I will leave you the link at the end of the presentation. I think this is a great resource. I have read this book when I was learning about deep learning, and I suggest you to do the same thing. But anyway, as you can see here, we have very complex functions, right, with a high level of nonlinearity. Even though if you want to use conventional models or algorithms from machine learning, it would be a challenge. It would be really, really complex to create a model, right, in order to tackle this problem, right? Okay. Now, on the left side, we have a neural network, right? And what we would do is that we would try to manipulate this variable. This variable is in function of the weights and bias, and try to approximate as best as we can, right? Then we try to increase. So my point is that this is what really happening behind the scenes, right? The backpropagation algorithms is manipulating, is changing the weights and bias, in this case age, right? Trying to minimize the cost function, trying to finding the most optimal parameters of the networks in terms of bias and weight, right, to diminish the distance, if you want to think in this way, the distance between the reality and our prediction. This is what's really happening underneath the hood, right? And this is why the universal approximation theorem is really, really powerful, because it doesn't matter how complex, how level of nonlinearity your function or your problem have, right? At the end of the day, there might be a potential neural network that can deal with the problem. And this is why the universal approximation theorem is so powerful. And to really be honest, the first time I heard or I read about the universal approximation theorem, I didn't believe it, because it felt like it was magic, right? So I remember that I created an example, right, very similar to this one. What I have tried in this example is to create a classification problem, and I use different methods, including logistic regression, and I think random forest. I don't remember. And I created my own neural network. I didn't use Python. I didn't want to use PyTorch. At that time, I didn't know how to use PyTorch, I didn't know how to use TensorFlow. I wanted to create everything by myself. So the network that you will see here, right, I built it when I was learning deep learning, right? It cost me a lot. And I would try to teach you how to build your own neural network in future lessons. But in here we have the most important functions, right? And as you can see, we have different data sets. This is synthetic data, right? With a lot of noise. I'm trying, this is a conventional classification problem. I'm trying to predict the red points and the blue points, right? That's it. But as you can see, if you have experience with classification problem, figuring out decision boundary, I think this is gonna be a challenge, right? Because they are both classes, they are merged too tight together. So it's gonna be, I mean, I did it on purpose, right? Because there's a high level of non-linearity in this problem, right? And finding a decision boundary is gonna be really complicated. You can change and alter the level of noise, right? I encourage you to do that, right? To convince by yourself. I generated the data, right? I created my own neural network. Everything is here. I will explain you that in future slides. And in this part I train my network. But let me show you first the decision boundary of logistic regression, right? I'm using scikit-learn here. My accuracy is 57%. 57%, right? You can see it right away. If you have any experience with classification models, you know that logistic regression isn't gonna perform really well, right? And I encourage you, maybe you can try with gradient boosting or maybe random forest, right? It's gonna be really hard to find a great accuracy for this particular problem. Then this is the decision boundary of my network. And this is a simple network, right? 2 hidden layers and that's it. I mean, I can increase the complexity of my network and probably I will improve this 84%. And that's the moment when I realize, okay, I am in front of something very special, right? Yeah, by the way, you can access this example in my repository, right? And try to enjoy this example because I think it opened my eyes the first time I tried. Well, now that you are convinced how powerful neural networks are, I hope, let's explore some concepts of linear algebra that we need before moving on to backpropagation. Okay, a vector. A vector is one of the most crucial aspects and concepts in linear algebra. A vector can have a dimensionality and an orientation. We can have row vectors and we can have column vectors, as we can see here in the image, right? Another important elements of vectors and operation, right? Adding and subtracting vectors. Right? We can do these operations as long as they have the same dimensionality. Of course, there's a special functionality that is called broadcasting. I mean, several people think that broadcasting is something that is coming from conventional linear algebra, but that's not true. This is something that doesn't exist in conventional linear algebra, right? I think that might be confusing. This is something that actually is being created in NumPy, right? And I think that's amazing. What broadcasting would do is that sometimes you have vectors with that one of their properties actually don't match, right? And as we can see in this image, we have 2 vectors, right? We have this one and we have this one. And what broadcasting would do is that it will try to fulfill the missing dimensions, right? In order we can add or we can subtract both vectors. At the end of the presentation, I have left some links, right? Because there are many rules of broadcasting that you need to understand before moving on. Now, the dot product. One of the most important properties in the entire linear algebra, focusing on data science, is the dot product. The dot product is one of the most important operations in all linear algebra. The dot product is a single number that provides information about the relationship between 2 vectors. If you are familiar with the correlation coefficient, right, the dot product between two vectors normalized is the correlation coefficient. There are several ways to indicate the dot product between two vectors. I will mostly use this one, right? It means transpose, right? And as you can see here, we got a number, right? This is the way to represent the dot product of two vectors. This is the geometric way to represent both products, right? There's a concept that is called cosine similarity, and it is coming from this formula. Okay, matrix and tensor, right? In terms of, if this is your first time in deep learning or complex neural network, maybe tensor is gonna be something strange for you. I'm gonna explain you what is a tensor. But before that, let's explore matrices. Matrix is a vector taken to the next level, right? As we can see here, we have a matrix. This is a 4x3. It means that we have it's a 3x4. We have 3 rows and 4 columns, right? As we can see here, this is kind of the different elements or components or entities that we have in linear algebra, right? In terms of dimension, first we have a scalar, then we have a row vector or column vector, right? Then we have a matrix, and then we have a tensor. A tensor is a matrix with a higher dimensionality, right? And that's very important, because when you move on to PyTorch or TensorFlow, right, there will be an entity called a tensor that will have an array of properties that will make your life much easier when it comes to dealing with complex neural networks. Okay, let's continue talking about matrices. There are several special matrices. You can pause the videos. These are some of them, right? You can pause the video and take a look by yourself. But we need to keep an eye on this one, right? Because we will use the zero matrix to initialize the parameters, the bias of our neural network, right? So let's keep attention to this one, because we will use it later. Now, in terms of operations, there are many operations, right? Including addition and subtraction, where you can add or subtract two matrices as long as they comply with the same size. When it comes to multiplication, there are several kinds of multiplication, including scalar and Hadamard, but we will pay special attention to standard multiplication, right? So let's explore this one. In here we have two matrices, right? We have matrix A and we have matrix B, and we have the result, right? So, but before moving on to the process of how to multiply both, we need to comply with certain rules, right? The thing is that the number of columns of the matrix on the right has to be equal to the number of rows to the matrix of the right? This is the main constraint, right? So the number of columns of this matrix has to be equal to the number of rows of this one. And the end result of both matrices, this is the end result, right? M by K. The dimension of this resulting matrix would be M by K, right? The number of rows of the left matrix by the number of columns of the right matrix. How do you multiply both matrices when they comply with the rules, right? The way I like to do it is I take the row of the first matrix, right, and I multiply that by the column of this one, right? So 2 by A plus 3 by C. This is the first element, right? Then then I move on to the second element, right? 2 by B plus 3 by D, right? As we can see here, and you do the same thing with the rows, with the second row, right? Okay, matrix and vector multiplication. You can multiply, right, a matrix with a vector, and we will see an example in the next slide how to do it, right? Okay, let's explain matrix and vector multiplication. If you remember the basic equation, right, in a vectorized way of linear regression, it is something like this, right? X, right, is our input, that, for example, let's say that in this example we have 1000 samples and we have 5 features, right? This is the dimension of our edge, and let's put it over here. And in terms of the weight, we will have one weight for each feature, right? It will be 5, 1, right? In fact, this we can multiply this matrix with this vector because they both comply with the multiplication rules. How is that? Right. Well, if we put this over here and we put this over here, right, we realize that the number of columns of the left matrix actually is equal to the number of rows of the right matrix, right? Even though this is a vector, but a vector, right, is just a matrix with a dimension of 1 in one of the rows of columns, right? So we are fulfilling the vector, the matrix multiplication, and at the end result of this would be, right, a column vector, which would be 1000 by 1, right? And if you are wondering about the intercept or the bias, that would be 1,1, right? This is when broadcasting comes into play, right? This is why we can actually add this vector together. That's why when you see some textbook, you will realize that this is the matrix X, then this is the vector, the column vector W, right? This is multiplication, and this is B. I'm sorry, this is B, and finally you will get a vector that is Y, a column vector that is Y, right? That's it. Now let's talk about calculus. First of all, we will examine important concepts such as the slope and derivatives. Then we will move on explaining the basic rules, power rules, and change rules in differential calculus. Then it will be really important to understand the exponential and logarithm, the derivative of the exponential and logarithm functions. Then we will give you an example of the derivative of the sigmoid function, and I'm going to explain how to derive this function, right? It will be really important because, as I explained in the beginning of this video, we will make an analogy between logistic regression and a simple neural network, right? And the logistic regression, one of the important pieces is the sigmoid function. Then I will explain maximum and minimum, partial derivatives, and finally gradient and gradient descent, right? Gradient descent is one of the most important algorithms in deep learning in general. The slope. Every time we speak about the slope and the derivatives, right, they are similar concepts, right? And the reason is because the slope tells us how much of a change in y we will get for any given change in y, right? For example, if we have an equation, right, if fx is equal to x, I mean we know that this is a parabolic function, and the derivative of this function is 2x, right? It means that every time we increase 1, right, we increase 1 unit in x, the function is increasing 2 in y, or 2 units, right? This is the magic of the derivatives, that we can find the rate of change in one specific point, and we will see an example later. If the slope is positive, then a positive change in x leads to a positive change in y. Right? On the other hand, a negative slope means that a positive change in x leads to a negative change in y, right? And this is the formula of the slope. Okay, in this example, I will explain some details of the slope and the derivatives, right? Again, you can access to this example just going to my repository, right? This is very simple. We have one function, right? 2x squared, right? And the derivative of this is 4x, right? If you know the rules of the derivatives of the exponential function, you will get down the exponents, right? And you will subtract 1, right? You get down 2 by 2, 4, and you subtract 1, right? Now, as you can see here, we can see the derivatives at different points, right? And the thing is that the rate of change in this function is different, and the magic of the derivatives, right, is that it will tell us at every point, the tangent line at every point, the rates of change, right? For example, if we add, I don't know, here 120, we have another slope, and the slope is steepest in each one of these points. This is different than a linear function. When it comes to a linear function, the rate of change is different. It doesn't matter in which point we are, right? And that's what we get when we find the derivative of a function. Okay, as I said before, the derivative, the slope of is the slope of the tangent line at a point x, right? This is known as the derivative. It tells us how the curve function is changing at the point of x, right? There are many ideas that we need to discuss, right? When it comes to the derivatives, the derivative of a constant will always be 0. This is the power rule, right? This applies for algebraic functions. As I said before, you get down the exponent, right? In this case, you will multiply by a, and you subtract one unit from the exponent, right? Another important rule is the change rule. When we have a function that is composed by two functions, right? We will see an example of this. The resulting derivative will be this, right? Will be this expression. I will explain this later. Okay, when it comes to the exponential, right, the derivative of the exponential with respect to x would be the same exponential, right? And this is like a generalization, right? For example, if we have x minus the exponential of x, right? We can apply this rule here because it would be, yeah, this would be the derivative. Why? Because the derivative of minus x will be minus 1, right? And we keep this same exponent here, right? Don't worry, I will explain that. Okay, in terms of the logarithm, the derivative of the logarithm x with respect to x would be 1 over x, right? And this is the generalization, right? This is when you have another expression here other than x, right? It would be the derivative of this expression divided by the expression, right? And in this part we can see the same derivative of logarithm but with another base, right? So try to keep this in mind. It's pretty much the same thing. Okay, let's explore this example about how can we derivate the sigmoid function, right? Yeah, this is our function, 1 divided by 1. Remember that we have something like this, right? 1, 0. This is the sigmoid function. In this part, if we want to derivate this, we need to apply change rule, right? Because we have two complex expression here. But what I do is I use another variable, u, right? And I equal that to one of the expression. And we know by the change rule that the derivative of the function x with respect to x would be, right, the derivative of the function nu, right, this expression, du by the derivative of mu with respect to x, right? Now, we know that the derivative of this expression, right, would be, this is a constant, so this is 0. Then we get down, the expression here would be minus 1, right? Remember the generalization, the derivative of the exponent here, and we keep the exponent, right? It would be this one. Okay, now we need to derivate. We have this now up to this point, right? Now we need to do we need to find, but which is right? And this is gonna be the same that minus 1. So if we try to derivate this, it would be minus, right? We by the power rule, it would be like this. And if, at the end of the day, would be minus, which would be translated to minus 1 square, right? At the end of the day, the final expression, right, would be dx a minus x divided by 1 square, right? This is the derivative of the sigmoid function. Something that you will realize, and that we will see later, is that if we say that the sigmoid function, right, is this, right, we can replace this expression, right? We can say, okay, the derivative of fx. We have finished our job here, right? Everything that I'm gonna say is in addition, right? But if you want to move forward, let's go, no problem. This is the derivative and that's it. I'm gonna simplify the expression and I'm gonna say, okay, this is, right? This is the same expression, right? But I can also simplify this. I can say that this expression internally would be 1, right? I'm sorry, let me delete this one. It would be 1 minus right? I mean, if you want, you can factorize this, but this expression here is equivalent to this one, right? Now, that's why you will see that this is what this expression is coming, right? When we will explain neural network, you will see that the end result of a neural network will be A equal to C, right? So this expression will become A1 minus A, right? But I'm just getting ahead of myself because I will explain this. The important thing to remember is that the derivative of the sigmoid function is this one, right? You can simplify it and you can get it to this part. Maximum and minimum. I think this is one of the most important concepts of the entire presentation, right? Because everything comes down to find the minimum of the function, right? And the parameters that will make our function gets to the minimum, right? For example, if this is w, we want to find what are the values of w where the function actually is minimum, right? This is important. A minimum is the place where the derivative of the points immediately to the left, right? These points here are negative, right? And the derivative of the points to the right are positive, right? So for example, here is the minimum, right? To the left, the slope is negative, and to the right, the slope is positive, right? Another important concept, right? When we get to the minimum, the derivative at that point, at that specific point, is 0. And we will see this concept. We will see that this is how we find it. We get to the we derivate a function and we equal the function to 0, and at that point, we will get to the minimum, right? We will find the values of the parameters of this function, the variables of the function that makes the function get to the minimum. Okay, let's explore this example where we get the minimum of a function. I would accomplish the results using 2 different methods, right? Okay, first of all, this is my function, right? 100 plus x squared plus 20x, right? The derivative of this function, right, is 2x plus 20. right? Okay, the minimum, right? How do we get to the minimum? Well, we find the derivative of the function, and then we equal right, the derivative to 0, right? Then we find the parameters. In this case, 2x plus 20 equals to 0, right? And x is equal to minus 20 divided by 2, and it would be minus 10, right? So this is my function, and minus 10 would be the minimum of the function. And actually it makes sense according to the visual information, right? We can see that the function is minimum to this point. Okay, I have another example. I get to the same results using gradient descent, right? And we will see gradient descent in further slides, but I wanted to explain this for particular reasons, right? The idea with gradient descent is that, right, we will get to the minimum by many tries, right? In this case, we find the derivative of the function, right? And then we choose any point, right? We are choosing a random point in the function, right? In this case, the random point would be between 40 and 50, right? It's over here. If we execute again, it will choose another point, right? And I did this on purpose. Then we will find the derivatives of the function, right? And we will subtract, and we will multiply this by a learning rate and subtract that from the previous value, right? So in other words, what we are doing is we are taking this random point, we find the derivative of the function, multiply that by a learning rate, a minimum learning rate 0.1, right? And we are doing this several times, right? We have here 100 iterations, right? And in the first iteration we get to this point, in the second one we get to this point, and so on and so forth, up to the point we get to the minimum, right? Why we are doing this instead of doing this, right? And I got asked this question several times, right? And it makes sense, and the reason why I created this example is because I want to explain the difference. Look at the result, minus 9.99, right? Very similar to our minimum. The thing is that I'm using gradient descent here because maybe in this example it doesn't make sense, but this is a simple function. We just have one variable here. What if we have a more complex function, a multivariate function with different variables, maybe 5, 10, 15, 20, right? Finding the derivative of that function would be really complicated. And that's when gradient descent comes into play, right? That we can find the partial derivative individually by each variable, and we can accomplish the same results, right? By iterating several times, right? This is the magic of gradient descent, right? This is why we are using gradient descent for neural networks, because when we have a neural network, we have different parameters. We don't have one or two, we have many parameters, right? And that's what everything comes down to, right? I can do the same thing here with negative value, right? Let's go with negative value. In this case, this is a random point. We get to the minimum again, right? We will see that when we get further, one of the things that we need to manipulate, right, is this learning rate. How long or how short these steps will be, right? I think it will determine how well our neural network actually will perform. Okay, let's explore the gradient. The gradient tells us how a function of more than one variable is changing. In the previous example, we have seen that if we want to get to the minimum of a function, it is really simple when a function has one variable. However, when we are in front of a function with 20, 30 variables, it would be really complex, get to the minimum. And I explained that. This is when the gradient and the gradient descent actually will help you out, right? And the gradient is like is the collection of the partial derivative of your function. For example, in here, right, the gradient, which would point to the direction of maximum change, is a vector containing the collection of the partial derivatives of our function. In this case, this function has three different variables, right? The first one is the derivative of the function with respect to s. The second is the derivative of the function with respect to y. And the third is the derivative of the function with respect to z. Notice that the notation is different. Okay, the gradient, as I said before, will tell us the direction in which the function is changing the most. And the opposite of this direction would be the minimum. That's why when you take a look, I mean, if you want to go back, you will see that I'm subtracting the derivative or the partial derivative, and that's why, because the gradient will point to the maximum. So if I subtract, I'm aiming to the minimum. We represent the gradient as the generalization of the idea of partial derivatives, right? In other words, a vector of partial derivative of a function. In the concept of function and optimization, a gradient is a vector that points, as I said before, in the direction of the gradient rate of increase of a function. Now we will see an example. Okay, now we will explore the example of gradient descent. Again, you can access to my repository to download this example. I'm not gonna go into all the different steps of this example. This is very simple, but I will assume that you have some previous knowledge of Python. The important thing is that this is my function, right? This is my function. I have two variables. In this case, finding the minimum by finding out the derivative of this function is not an option. I need to use gradient descent to get to the minimum in this case. In this function, I'm determining the partial derivative of x and y, and I'm storing this in NumPy array. Okay. In this part is my algorithm. I find the gradient, and I will subtract the derivative. I mean, first of all, I will choose a random point. In this case, I will choose this point, right? But this is a random point. This is a random function from NumPy, and then I will find the derivative with respect to x, the partial derivative with respect to x and with respect to y of the c function. This is my function c with respect to x and y. Then I will subtract in different iterations each variable, and then I will execute. One question that I've been asked is, what if I don't have enough iterations? You can test it, right? If you don't have enough iteration, we won't get to the minimum, right? We won't get to the minimum. The minimum of this function. Imagine this is a valley, right? Or this is a mountain. The bottom of the mountain should be around here, right? See, if you don't have enough iterations, you won't get to the minimum. That's why you need enough iterations. Another question is, and you can test by yourself. But what if I don't choose a correct learning rate? For example, if you choose 5, I don't know, you won't get to the minimum. Look at this. Look at all these jumps. We are not getting to the minimum. That's why the correct learning rate is important. If you don't have a proper learning rate, the gradient descent will not converge. And when you get further in deep neural and in complex neural networks, you will see that we call these hyperparameters, and you can optimize your hyperparameters. Sometimes it's not that easy to choose the correct learning rate. So this is the idea of the gradient descent. Again, you can actually play with this. You can choose other random initialization points, maybe here or here, and it should converge to the minimum. Okay, let's move forward. As I said before, the gradient descent is an optimization algorithm used to minimize a function by different iterations in the steepest descent. That's the idea. The goal is to find the minimum of the function, which corresponds to the lowest point in the landscape. This is the example that I was explaining you. If you are here in the top of the mountain, when you find the gradient, let's remember that the gradient is a vector with this is our function with respect to x in our example, with respect to y, and the gradient will point to the direction of maximal change. But if we subtract the gradient of each one of our variables, then we will move in the opposite direction, and we will do this several times by a learning rate. Now let's talk about logistic regression. Up to this point, we have explored the different concepts of linear algebra, calculus, and gradient descent. Now is the turn to talk about logistic regression. Why? Because at the beginning of the video of this presentation, we mentioned that we will make an analogy between logistic regression and a simple neural network. It will help us to understand the principal concepts of backpropagation and a simple neural network. Okay. Before we dive into backpropagation, let's build a solid foundation of understanding logistic regression. It turns out that logistic regression can be seen as a very small neural network. We have the input here, we have the weights, we have the bias, and we have the output. And the output is a sigmoid function. Okay. Logistic regression is a statistical method for predicting binary outcomes based on one or more predicted variables. If you have explored in machine learning logistic regression, you know what I'm talking about. It models the probability that a given input belongs to a particular class, positive or negative. Think of logistic regression as a single neuron in a neural network. It takes the input, it applies the weights and bias, and it passes the result through an activation function. Okay, we need to bear in mind that we need a sigmoid function when it comes to logistic regression. Why? Because when we have a binary classification problem, we are predicting a probability between 0 and 1, and the sigmoid function will squeeze this value. The sigmoid function is the magic function that lets us get the desired probability as an output. It does this by squeezing any value to fit between 0 and 1. Similar to linear regression, we have weights and bias. The idea is that we want to find the optimal values between for weights and bias to minimize the function. We first multiply the inputs with those weights and add it to the bias. And the end result would go into the sigmoid function, and we will get a probability between 0 and 1. In this presentation, we will focus on a classification problem, right? But we can go further. You can go further to take these knowledges to a multi-class problem. And these weights and bias are chosen randomly at first, but the gradient descent algorithm will make sure that these parameters are updated in order to find the minimum of the cost function. Okay, we want to find the most optimal parameters that will minimize our cost function the most. This is the equation of the logistic regression. As we can see here, this is the equation. And we have C here, and C is in function of W and V. In other words, we want to find the weights and bias that will make our function to minimize the most. Okay, the loss function for the logistic regression is this one. I'm not going to explain how to determine this. I think this is out of the scope of this course. but you can test me and I can explain you why this is the equation for the loss function of this binary classification problem. Okay, but the thing is that this is a loss function for one sample, and of course the cost function is the summation of all the different results. What we want to minimize is this thing. This is what we want to minimize. Now, okay, this is our sigmoid function. The idea is to find the best possible parameters of W and B. Let's see an example. Okay, let me explain to you how gradient descent will find the optimal parameters of our sigmoid function. Here we have W and B. This application, you can access this application in my repository. Just bear in mind that you can't execute this in Jupyter. This is a Streamlit application. You need to do it in your console. Okay, now I'm gonna answer two questions here. The first one is how gradient descent actually will find these optimal values. As you can see here, these are the real positive point. This is the reality. We have in this part the negative point. So the whole notion is to find the best possible curve to maximize the probability of the observed data. What do I mean by that? Okay, let's see that we have these values. As you can see, these are positive values, but our model is predicting like 0.7. Now, if I move this is much better, but because now for these points I have a higher probability, and this is what the model would do. This is the maximum likelihood estimation. That's why we have a negative symbol, and this is the second answer. This is the second question I'm gonna answer, because I get asked why in the loss function we have a negative symbol in front, because we are trying to minimize the function, but what we have here is the maximum likelihood estimation. We are trying to maximize the likelihood of the observed data, right? We have the negative symbol because we will minimize the cost function, and that's the idea. This is what the gradient descent actually will do. It will try to find the optimal parameters in terms of W and B that would try to get closer to the reality. Okay, now let's find the derivatives of the different parameters in order to optimize our function. As we mentioned at the beginning, this is a loss function. This is the sigmoid function. We have the sigmoid function here, which is the same thing that our loss function is this one. Minus. This is our loss function. We want to minimize that. But we want to find W and B. We want to find the most optimal parameters of W and B. And we know that because of this relationship, because W is in function of C and C is in function of A, we know that we have a change rule playing around here. But we will go step by step. The first thing that we want to find is the partial derivative of the loss function with respect to A. This is the first thing we want to find, and then we will go step by step. We will call this L1 and we will call this L2. So let's find L1. L1 would be y log of A, right? And we know that the derivative of L1, the partial derivative of L1 with respect to A would be y divided by A. You can go back to the slide in the calculus, right? This was 1 over A, but because of this is a constant because of the partial derivative, then we have our first expression, our first partial derivative here. Okay, we have L1. Now let's go to L2. L2 would be log of 1 minus a minus y log of 1 minus a. We know by the chain rule that this is the derivative of the inside by the derivative of the outside. In other words, and here we have y log, I'm sorry, 1 minus a. Or we can, I'm sorry, this is plus, right? Because the derivative of the inside is minus 1, and we multiply this, right? So at the end we will have minus 1 plus y 1 minus a. Okay, now we have second term, and we have a negative symbol here. So at the end of the day, the partial derivative of the loss function with respect to a would be minus y divided by a, and at the end it would be plus 1 minus 1 minus a. This is gonna be the derivative of the loss function with respect to a. Now we have our first puzzle. Now the second step would be, we want to find the derivative of the loss function with respect to c, and it would be the derivative, because of the change with the derivative of the loss function with respect to a by the derivative of a with respect to z. And that's the idea. Yeah, we have this part. Now we have to find the second part. Okay, so we have step 1 completed. Now we want to find the derivative of L with respect to C, and we say that we have to change rule again here. This is the derivative of L with respect to A by the derivative of A with respect to C, right? And we know that A, it would be sigmoid of C, and we know that the sigmoid function is this one, right? So what we want to, we need to find the derivative of this. Remember that we actually found this, but let's do it again, right? If you remember, go back to that slide. The derivative of L with respect to C in this case would be this. This is the derivative of the sigmoid function, and we said that this is equivalent to 1 by, I'm sorry, by this expression, and this can be translated in sigmoid of C, 1 sigmoid of C, which is the same thing that A minus A. So we can say that the derivative of L with respect to C would be A 1 minus A, right? And this is a step 2. Okay, now we have completed the first step, second step, and now we want to find the derivative of the loss function with respect to C, which is the derivative of L with respect to A by the derivative of A with respect to C. And we have both here. So in this case we have A 1 minus A multiplied by minus y 1 minus y This is the expression, right? Okay, now we will multiply this by this and then this by this. Okay, and then we will have a1 minus a. This is gonna be our first term plus a1 minus a 1 minus a, right? This a is and this one is gonna go with this one. So at the end of the day, we will have minus plus if we multiply this, we will have I'm sorry, this is y and this is minus a y. This is eliminated, and at the end of the day, the derivative of L with respect to dc would be a minus y. This is the partial derivative. Okay, now we have completed step 1, step 2, and step 3. And the final step is to find the derivative of w and b. We know by the chain rule the derivative of the loss function with respect to w would be the derivative of the loss function with respect to a by the derivative of a with respect to c by the derivative of c with respect to w. Yeah, we have found this part, right? It turns out that this is the derivative of the loss function of c, right? This is the derivative of the loss function with respect to c, right? So we just have to find this part. We know that c is equal to wx plus b. If we want to find the partial derivative of d of c with respect to w, in this case, this is a constant, this is going to be 0, and at the end of the day, it would be x. It would be x. So, at the end, the derivative of the loss function with respect to w would be the derivative of the loss function with respect to z by x, or in other words, I'm a minus by x. This is what everything comes out. And when it comes to the bias, it is much easier, because the bias, again, we have this, the derivative of the loss function with respect to the bias would be it would be the derivative of the loss function with respect to c by 1, or in other words, I minus this is, yeah, this. So by these two equations, now we know how to find the optimal parameters of w and b with respect to the loss function. One more thing before moving on to the last part of the presentation. What we did was to find the parameters for the loss function, but at the end of the day we want to find that for the cost function, the summation of all the loss. And I wanted to show you this here. We are doing this sample by sample, even though when we go to the code and the construction of our neural network, we did it with a vectorized version, but I'm going to explain that later. We can see how the derivative of the loss function with respect to c, and in this case we have two different parameters for w, and at the end of the day we compute the loss function and the derivatives in general for every weight and the bias. Again, we would use a vectorized version because we will not do this sample by sample. Now we are getting to the end of our presentation. We are getting ready for backpropagation. Initially, we explored the different concepts of linear algebra. Then we move forward, explaining calculus and the different derivatives. Then we take a look at gradient descent, the gradient and gradient descent, and finally we found the equations for finding the most optimal parameters for a logistic regression model. We said that hidden unit and an output hidden unit actually is very similar to a logistic regression, and we found the equations and the process is very similar. And now we will explain. We will give you the neural network representation we will be using for backpropagation explanation. Then I will explain the different activation functions. After that, I'm gonna introduce backpropagation, and finally, I will provide you with the neural networks that we would use. Like an example for explaining backpropagation. The first one would be a one hidden layer example, but the final algorithm can handle any kind of hidden layers, right? Any number of hidden layers. It can be a very complex neural network. You can pause the video and take a look at these notations. These notations I will be using throughout my presentation. So take a look by yourself, pause the video. Right. Now, this is a very simple neural network representation. We have, in this case, the input layer, the hidden layers, and the output layer. In this case, we have 3 nodes in the input layers. Most of the time, when we talk about the number of layers of a neural network, we said that we have 2. We don't count the input layers, right? So bear that in mind. In this case, we have, for the hidden layer, we have 4 nodes, and for the output layer, we just have 1, because this is gonna be a classification problem. If we had a problem with multiple classes, for example, if we want to predict digits, right, from 0 to 9, we will have probably 10 outputs. But in this case, we are predicting 1 or 0, a positive or negative class, so we have just one output unit in this case. These are the equations for this output unit. In this case, this is the linear representation, and this is the output, right, a sigmoid function, very similar to the logistic regression convention. Okay, activation functions. As I explained many slides previously, each unit here has an activation function or a step function, right? For this kind of problem, classification problem, we will have a sigmoid function here. However, most of the time, at least in this presentation, in reality, in most of my problems, I will use a ReLU function here. And the reason is, I'm not gonna go into more detail about this, but the thing is that initially we were using sigmoid functions, but one of the breakthrough over the past several years is to replace the hidden unit step functions with ReLU or tangent, most of the time ReLU. The reason is that when the value of C actually was very high, the gradient was not converging because the derivative actually becomes 0 in this part, right? Something that doesn't happen with the ReLU function, right? And this is the reason. And overall, I've been using sigmoid function for output layers and ReLU functions for hidden units. Now, I hope that you became familiar with the notations I would be using, but this is very simple, right? In this case, I have this this neural network. I have, in this case, I have 2 inputs. I have 4 hidden units or 4 neurons for my hidden layers, and I have 1 output, right? I will be referring to this layer with the letter L, right? And it would be my first layer. So, for example, in this case, I have C1 here. C1 for the layer 1 would be W1 multiplied by X, right? This is the input plus the difference is that this is not a vector. If you remember, when I was explaining linear regression at the beginning of the presentation, I was explaining that this was a column vector. But for this case, this is gonna be a matrix, and the dimension of this matrix would be the number of nodes of the hidden layers by the number of inputs. So we will have just one matrix that will store the weights of each one of these units for each one of these features, right? And this is what that's why vectorization actually is beautiful, because it will simplify things. And the same thing for the bias, right? Very important information. Here is the summary. In this case, we have the equations for the hidden layers, or the first layer, and we have the equations for the output. Now let's begin our journey with backpropagation. First of all, I will give you an introduction of this. Then I will speak about 2 important concepts that will help us to train our network. In this case, forward propagation and initialization. You will see that first of all, we will initialize the parameters of our networks, our bias and weights, and then we will perform forward propagation. After that, we will perform backward propagation and then update the parameters of our network. That's like the cycle that we will be implementing in terms of training our neural network. I will explain step by step, but that's the whole idea. We need forward propagation and initialization besides backpropagation for training a network. Then I will present 2 examples. The first one would be a simple neural network with 2 layers, and the second one will be an algorithm that will be able to manage any number of layers. Now, backpropagation is currently the core algorithm behind deep learning. This algorithm was created in the 1980s, and I think this being one of the breakthrough of the entire ecosystem of deep learning. I believe that practitioners of deep learning need to understand what backpropagation is. I think they need to understand the foundations of this algorithm. We know training a neural network involves a loss function. Yeah, we know we spoke about that. This function actually would try to minimize the cost, trying to find the most optimal parameters in terms of weights and bias for the different layers of our network. When we do gradient descent, we will use the gradient to decide how to move from one part of the loss landscape to another to find where the network actually perform best. The goal of the training is to minimize the loss function or the cost function over the training set. Backpropagation is the algorithm that tells us what the weight and bias, right? The weight and bias of the network should be. With the partial derivatives that we saw in many slides previously, we can apply gradient descent to improve the network performance on the next pass of the training data. Now I will be introducing the network or the structure that I will be using for explaining backpropagation and determining the different equations and that will help us to optimize the weight and bias. This visual diagram might be overwhelming at the first time, but don't worry, I will explain each step. First of all, we have in this part we have our input, right? We have in this case 3 features. Our input layer would have 3 hidden units, and in this case we will have 100 samples. The shape of our input would be the number of hidden units or features and the number of samples, right? Yeah. We would use this variable to indicate the number of inputs, and m would be the variable that actually would indicate the number of samples. Okay, this is our input layer. Now, this is our first layer. We will call this L1, and this is our first layer, and this is our second layer. It would be L2, or you can say this is the hidden layer, and this one is the output layer, right? Okay. Now, each layer has weight, a matrix of weight, and a matrix of bias. The weight of this layer would be represented by W1, and the bias will be represented by B1. The weight of this one would be represented as W2, and the bias by W2, right? Remember that when we were talking about logistic regression, I was mentioning that this was a vector, a column vector, but now in the vectorized version, the weight and bias of each layer will be represented as a matrix. This is much easier. It will be, we will understand much faster how the network actually operates in this way, in this vectorized way. Now, okay, we have the input. Now, C would be the entry of our hidden layer. That would be our weight and bias. Yeah. The shape of our weight would be the number of hidden units. We have 4. And the number of features, or the number of input nodes, and this and as you can see here, this dot product actually fulfills the rules, because the number of columns here actually is in alignment with the number of rows, and at the end we would get a matrix that has this dimension. And if you are wondering how we can add the bias, because the bias would be another matrix with the number of layers here and 1, and this is possible because of broadcasting. This is a functionality that I explained before that exists in Tensor and in NumPy, right? Okay, then the output of our hidden layer would be this matrix A1, and we will have this. We will have A2 here for our second layer, right? Okay. You know that each hidden unit has an activation function or a step function. I will use the hyperbolic tangent for my hidden units. Sorry, I think I misspelled this. This is the hyperbolic tangent activation function. And when it comes to the output, you know that we will use sigmoid function, right? So the output would be the hyperbolic tangent of the entry, and in this case, the output of the second layer would be the sigmoid function of the entry, right? Now, there are one important element that we need to take a look here. Z2 would be the weight by the entry plus the bias, but this entry is the same as the output of the previous layer. That's why I'm defining Z2 as W2 by the output of the previous layer by plus the bias of this layer. And that's the way we connect one layer to the next layer. Okay, before moving on, I would like to remind you something. All what we are trying to do here is to find the parameters of our network. That's it. All the equations, all the different elements and components that we have been exploring up to this point is to find the weights and the biases of each hidden layer output layer. That's it. Of course, we would use the cost functions. We would try to minimize the cost function, and at the same time using gradient descent to go step by step to find the best weight and bias for each hidden unit. Backpropagation would do this automatically, right? And I will show you how it would do it behind the scenes. But that's the idea. We are trying to find the best and the most feasible parameters of our network. Okay, let's go to the next part to determine the equations. Okay, let's go. Let's determine the equations for backpropagation. First of all, we will begin with this layer, then we will move on to the previous layer. Right? If you remember at the beginning of the video, I addressed some aspects about neural networks, and one of the things that I mentioned was that we can create an analogy between logistic regression and an output unit. We mentioned that the output of logistic regression was given by the sigmoid function with the entry, and this entry was the weight by the input plus a bias. We also define a loss function to minimize these parameters, and this loss function was y log of a plus 1 minus y log of 1 minus a, right? And based on this, we get to these parameters because we mentioned that the partial derivative of the loss function with respect to w was the partial derivative of the loss with respect to a by the partial derivative of the a with respect to c by the partial derivative of the c with respect to w, because we have a change rule here. W is in function of c and c is in function of a, right? We get to many conclusions. You can go back and you can take a look at the equations. But the first derivative that we found was the derivative of the loss function with respect to a, if I remember correctly. Let me check. This is exactly. Let me check. Yeah, exactly. This is the partial derivative with respect to a, and the partial derivative with respect to z was a minus y, and the partial derivative of the loss function at the end of the process was the derivative of L with respect to c by the input, and in case of the bias, it was the derivative of L. The derivative of a by the bias was the derivative of L with respect to c, and that was it, right? That was the whole idea. And then we just have to update the parameters of we have a learning rate here, and the derivative of the loss with respect to weight, and in case of the bias, this symbol is accumulation. Learning rate, derivative of L, derivative of B, right? We would do something similar in this case. The only difference between logistic regression and this approach is that we would use matrices, because we have different layers, and in these layers we have different units. In case of logistic regression here, for the distribution we just have 1 unit. However, in this layer we have 4 units. That's why if you take a look at my video, at the previous slide, I mentioned that we will have here the number of layers by the number of inputs. Right? This is gonna be the dimension of our weight. Right. So let's begin from this point. We know that the output of this layer will be A2, the entry will be C2, the output of this one would be A1, and the input would be C1. Right? Okay. So let's define this over here. Yeah. Okay. Now A2 would be the sigmoid function of Z2, and we want to find, of course, the weight, these weights and these biases. We know that the derivative of the loss with respect to A2 would be minus, and this is a vector. Let me express that like that, and this is a this is a matrix. This is the equation, and I will express this as dA2, right? I think it's more simple. Then the derivative of L with respect to dz was well, but let me go and step back. Yeah, the derivative of the loss function of A, because of the change rule we need this, of A with respect to z2 was, if I remember correctly, A2 1 minus A2, right? Okay, and I will represent this as dc2. Okay, the derivative of the loss, no, sorry, I will represent this in I will represent this as dA dc2, right? But we will not use too much this one. And the derivative of the loss function with respect to z2 was just A2 minus y. And I will represent this derivative as dc2, right? So let me try to summarize, right, the important equations. The most important equation here would be this one, dc2, and dc2 would be A2 minus y, right? And using dc2 we will find dw2, and dw2 would be dc2 by x, but x here, right, the entry of this layer is the output of the previous layer, it is the output matrix of the previous one. So if in this case it would be L minus 1, or you can say dc2 by A from the previous layer. This is gonna be very important equation, and the bias, as you might guess it, would be dc2. Okay, here we are presenting the equations of that we determined in the previous slide. This is with respect to the loss function, and this is pretty much the same thing, but in terms of the cost function. As you already know, here we are computing the dot product, and we divide that by the number of samples, and in case of the bias, we are summing this and dividing by the number of samples, right? But again, these are the equations that we determine for this part, right, for the output unit. Now we will calculate the equations for weight and bias for the hidden layer. Okay, let's go. Now we know how to optimize W2 and B2, right? Now we want to find W1 and B1. We want to determine the equations, right, the derivatives, to find these values with respect to the loss function. Okay, in general we know that the derivative, this is what we want to find, right? The derivative of the loss function with respect to W1, it would be the derivative, the partial derivative of the loss with respect to with respect to A by the derivative of A with respect to C by the derivative of C with respect to W, right? We also know that this is the derivative of L with respect to C, right? So we need to we need to find the derivative of the loss function with respect to C1, right? This is one of our objectives. Okay, now the derivative of L with respect to C1 would be the derivative of the loss function with respect to with respect to A1 by the derivative of A1 with respect to C. I think my pencil is acting up. That's the idea, right? That's the idea. Now, in this case, how can we find A1, right? We know that the output of this layer, right, A1 here, would be the input of the next one. And in other words, C2 is equal to W2 by A1 plus the bias, right? Because we need to find, right, the loss function with respect to A1. Okay, and this is how we can do it. The derivative of A1, the derivative of the loss function with respect to A1 would be because A is just one parameter, you will see that the derivative of A1 will be very, very similar to the derivative of the weight, right? Remember that the derivative of the weight is DC2, DC1 in this case, plus A1. That's it. You will see that we would get DC2, and you will see that we will get to the similar conclusion with respect to A1, that it would be the derivative of C2 by W2. But let's find this out. It would be the derivative of the loss with respect to A2, derivative of A2 with respect to C2 by the derivative of C2 with respect to I'm sorry, not W, with A1, right? We know that this is DC2, right? The derivative of C2 with respect to the A1, if you find the derivative of this, it would be W2, because B is a constant, right? and at the end of the day, dA1 would be dC2 W2, right? That's the way we found it, right? Now we have the first we have the derivative of the loss with respect to A1. Now we need to find this one, right? Okay, let's delete this to make some space here. Okay, let's do it over here. Yeah, and we have the equations over here. We have the equation. Let's put it over here. dA1 is dC2 by W2, right? Okay. Now dA1 with respect to C, right? Here we would use an hyperbolic, a tangent hyperbolic function. If you explore or read some textbook information, you will see that you will find this equation. This is what you will find, right? The derivative of the function. But in this case, g, right, would be the hyperbolic tangent, and the derivative of the hyperbolic tangent is 1 by the, let's say, of x, it would be the tangent hyperbolic of x squared, right? So at the end, dA1 with respect to I'm sorry, this is partial derivative with respect to would be 1 minus the hyperbolic tangent of C1 this is a square, right? So at the end of the day, the derivative of the loss function with respect to C would be, right, this expression dC2 by W2, right, and we multiply that by 1 minus the hyperbolic tangent of C1, and this is a square, and we close brackets, right? And now we have the derivative of the partial derivative of the loss function with respect to C, and we know that the derivative of the loss function with respect to W1 would be dC1 by the entry. And that's it. This is how we can connect everything together. The same cycle would repeat over and over again. It doesn't matter how many hidden units we have in our network. Now we will see a summary of the whole process in a different slide. Now this is a summary of the equations that we were calculating in the previous slide. You can pause the video and take a look by yourself. Before going to the example in Python, let's take a look at another topic, and that's it. Okay, this is the sequence of activities that we will follow for training our neural network. First of all, we will initialize the parameters of our network. Then we will perform forward propagation, right? Then we will execute backward propagation, update the parameters, right? And this process will be repeated several times, right? We will have a certain number of intervals, and then after that we will make a prediction of certain values, and that's it. So let's go to the examples right now. Now I will show you how I created my own neural network using the equations that I explained to you in previous slides. Okay, this is the problem, this is the exercise I was showing you at the beginning of this presentation, and it is about predicting, this is a classification problem about predicting one of these two classes. If you remember, we have a lot of noise here, and this is really complex. We tried different classification algorithms, and we also created a neural network. Okay, let's explore how we created this network. Okay, first of all, I will explain the most important functions. The first one is the initialize parameters. I'm initializing, we have two layers, right? I'm initializing every weight of each layer. In this one, I'm using this random function and I'm multiplying that by 0.01. And in terms of the bias, I'm using the zero matrix. I'm storing that in a dictionary called parameters. In this part, I'm defining the hyperbolic function that I'm using for the hidden units, and the sigmoid function that I'm using for the output unit. Right, very straightforward. In this part, I define the different activities of the forward propagation. Right, as you can see here, I define the linear results of the weight and the input. Right, this is the dot product. This is the dot product of the weight for the first layer and the input, right? And we add the bias. Then we pass that through the tangent activation function, and we get A1. We do pretty much the same thing, but we are using the sigmoid function here, and of course the entry for the output layer would be A1, right? The output of the previous one. And I store this in a dictionary called catch. This is the function for the cost, right? For the cost of the network, right? You should be familiar with this equation. And in this function, I perform backpropagation, right? The first thing is that I get the initial values that I process in forward propagation, and the first step is to calculate dc2, right? The derivative of the loss function with respect to c2, and it is a2 minus y, right? As we explained in previous slides. Then I calculate dw2, the derivative of the loss function with respect to w2, that is dc2, right? By the entry, in this case A1. We are using the dot product and the transpose of A1, right, in order to comply with the matrix rules. In terms of dv2, it is the summation of dc2, right? Very important that we use keep dins. Sometimes we need to indicate that to numpy to keep the dimensions of the matrix. Now we have dc1 here. dc1 would be w2 by dc2 multiply, and this is element wise multiplication by 1 minus the power of a1. You could do two things here. I mean, a1 here is the hyperbolic tangent of c1. You could put this over here, and that's it, right? And you would get the same results. But what I did was I stored this in a catch, right? I stored this in a variable. But at the end of the day, it's the same thing. I'm mentioning this because that might be confusing, because it's not the same equations that we described in the PowerPoint. But what I'm doing is the same thing. You could take this one and put it over here, and you will get the same results, right? At the end of the day, I studying the derivatives of dw1, dw2, dv1, and dv2 in grads, right? And I would use the results of the backward propagation to update the parameters, right? As you can see in this function, I will receive the gradients, and I will subtract the gradients or the derivative of the weight of every layer, and I would subtract that from the parameter by a learning rate, right? And in this function I create my network, I create my network, I specify the number of iterations. I have a lot, by the way, 10,000 iterations. And first of all, the first thing that I would do is to initialize the parameters. You need to initialize the parameters, right? And then you perform forward propagation. You have a cost, right? After you perform forward propagation, you have a cost. In the first iteration, this cost, of course, is going to be high, but that's the idea. Then we call backward propagation. In this part, I have the gradients, I have the derivatives, right? And I will update the parameters using the derivatives of the backward propagation function, right? And I will print the cost here. And the network will optimize the value in each iteration, right? Remember that the gradient, imagine that the gradient is like when you are in a mountain and you want to get to the bottom of the mountain, right? That this is what we are doing here. And as you can see, the cost of the function is reducing in every iteration, right? And we have 0.02. And at the end, this is our decision battery. This is an implementation of 2 layers, right? You can access to this example in my repository. I have another example here when I built. I pretty much use the same concept, but you have any number of layers in this example. In this part, I'm using the MINS data set to predicting digits from 0 to 9. But here you can use any number of layers or hidden layers in your network, right? Try to take a look by yourself. I think this is a great implementation. At the end of the day, these examples, they are great for understanding the concepts of neural networks, but in reality, you will use PyTorch or you will use TensorFlow, right? The important thing is that you know and grasp these knowledges. Okay, let's go to the conclusion of this presentation. Okay, this is the end of my presentation, backpropagation in neural networks. I really enjoy providing you with all the different knowledges and the different materials throughout this presentation. You can find more information about the examples that we were exploring in my repository. Thank you.